So today we're going to be talking about summation notation, sigma notation, excuse me. That's how it's presented up here, sigma notation. It's also referred to as summation notation. I typically refer to it as summation notation just because that's kind of what we're doing conceptually. So do you see here, the reason why I call it summation notation is because between like A sub 1 and A sub 2, there's a sum, right? And then you're just adding and adding and adding and adding and adding. That's what's going on conceptually here. So that's why I refer to it normally as summation notation. Basically what this means, it's like you have the summation from I equals 1 to n of A sub I, and that equals like A sub 1 plus A sub 2 plus A sub 3 plus A sub 4. Basically what that means is what we're doing is sigma notation indicates the sum from I to n. So you start at I, and then you go all the way up to n. And between those numbers, you're like adding up everything in every part of the series. Okay? So if this was like... Yeah, I did.
Oh, it's good.
Yep. So basically, if this was like the summation from I equals 1 to 3 of I, that would just be 1 plus 2 plus 3. You start at 1, and then you go all the way to 3. And that's just going to equal 6. That's all it's going to do. That's what summation notation means. Okay? Now, we use counting numbers. That's important. So counting numbers are 1, 2, 3, 4, 5, 6, 7, 8, like all the numbers that appear in nature. Sometimes you also start with 0, but the only time you would start with 0 is when I equals 0. That's when you start with 0. Technically, theoretically, you could start off with a negative number if you wanted to. Most of the time, we don't do that, though, with these. But it is hypothetically possible to do that. Okay? But we don't. So you don't need to worry about it. So here's some examples down here, like C, D, and E. Sometimes they give you, sometimes they'll give you like a function, like this j squared from 3 to 7, the sum of that. So every place you see a j, you just plug in the number that you're on. So here we started off with 3, so it's 3 squared. Now we move on to 4, plus 4 squared, plus 5 squared, plus 6 squared, plus 7 squared. That's what's going on here. You have this function here that you can go with, and then you can add up all these terms, and that'll be your answer. Okay? Same thing down here, from 1 to 5. 1 over square root of j, and then it's like 1 over square root of 1, 1 over square root of 2, 1 over square root of 3, 1 over square root of 4, 1 over square root of 5, and then you can add all those numbers up together. Okay? That's what's going on here. This is, like this part in here, this is sometimes referred to as a series. You might hear it that way. In Calc 1, we're not going to get majorly into series, but like if you get into Calc 2, you'll start talking more like Taylor series or stuff like that. So that does exist. That's out there in the world. Okay. Now, when we get down to like E, you guys notice how there's an N and there's a K, right? You notice how it's from K equals 1 to N? So every place we see a K, that's where we can change the number. But we don't actually change the N. Does that make sense? Down here, this is more like a general formula, we like to refer to it as, because we don't have like an actual number up top. Like up here, we don't have an actual number. So we have to go to a general expression, which is just this one down here. That's what that means. Okay? This k equals 1 is sometimes referred to as a lower bound, and this n is sometimes referred to as an upper bound. So just kind of keeping that in mind, like understanding what the notation is from there. Are there any questions in general about like how sigma notation works? Or is it seems pretty straightforward and clear?
So why don't we change the N though? Because there's nothing for
Yeah, because we're referring to K as K changes, not as N changes. Yes, since k is on the bottom, that's the number you change. You don't change n. Okay? That's what that means. Okay? Any other questions? That was a good one. Okay. If not, summations and sigmas, summations do have a couple different properties. So, do you see out here how this k right here, that refers to a constant, okay? That wasn't a pun intended. Okay, it's too late in the day. You guys don't get my jokes. So basically what that means is we can pull the k out and then just take it times the summation. That's totally legal. We can do that. Like, no problem whatsoever. Okay? Now, the second one, we can split up the summation as well. So do you see how, like, this is the summation of the thing all together? Sometimes it's easier to do the summation of everything individually. So do you see that? And here, on the left-hand side, we're taking the sum of, like, the whole thing all at once. Sometimes it's more advantageous, though, to break it up into two different sums and find it that way. Okay? It's totally legal. We can do it. Okay? Makes sense? Sort of, kind of, maybe? Yep. Getting there? Okay. Cool. So let's do some examples. Now, since the time change and it's the last period of the day, instead of going all the way to 5, I think that's a typo. And we're just going to go to 3. All right. I know, it made a typo. My bad. I'm sure I put 3 when I made this. So we're going to go from I equals 0 to 3. Okay? So that just, but wait, time out. Before we even start, we can make our lives easier somehow. Yeah. Do you see how 2 is a factor of both of these? So we can just pull it out. 2, the sum from I equals 0 to 3 of I plus 5. Do you guys see that? I kind of took a liberty. Instead of having like the 2 distributed, whoa! Oh no, we're good. Instead of having the 2 distributed there, I just pulled it out right away. Does that make sense to everyone? Or would you rather I show that step? It's your guys' choice. Oh, we good? Okay, sweet. So now this is this new thing right here. This new sum. This is what we're finding the sum of now. Okay? So now I can just replace that with stuff up here. Okay? Following kind of the rule that it has going with it. So that's just 2 times 0 plus 5 plus 1 plus 5, whoa, plus 2 plus 5 plus 3 plus 5. Okay? That's what's going on here. Now I can simplify this down. That's just the same thing as 2 times 0 plus 5, that's just 5, plus 6, plus 7, plus 8, 5, 6, 7, 8. Who do we appreciate? Who? All right. So yeah, now we can simplify one step further. 11 plus, like 5 plus 6, that's 11. 7 plus 8, that's 15. So that's just 26. So 2 times 26, that's 52 if I'm not mistaken. Someone want to check me?
You're right.
I'm right? Okay. Sweet. So this is 52. Okay?
Is it going to be that simple? Or
For these, yeah, that's simple.
how about this?
For the good chunk of the assignment, I think it's pretty simple. But when we get to the back side of this page, things do get, yeah, they get trickier. The last class did not like me when I got to the second half of the page. Okay. So yeah, that's how that operates. Now we can move on to the second one. Now, technically, we could rip it apart if we wanted to, but this one is simple enough. Do you guys want to? No, I don't. I don't feel the need to. There's nothing I can simplify out, so I'm just going to go for it. Okay? So I start at 1. So that's just like 1 squared minus 1 plus 2 squared minus 1 plus 3 squared minus 1 plus 4 squared minus 1. Okay? Now I can simplify this out. 1 squared minus 1, that's just 0. 2 squared is 4, minus 1, that's just 3. 3 squared is 9. 9 minus 1, that's just 8. 4 squared is 16. So 16 minus 1, that's just 15. So now that's just like 11 plus 15, because 3 plus 8 is 11. So 11 plus 15, that's just 26. And that's our answer on that one. Make sense?
Oh, yes.
Yep. Okay. So now moving on to the back side of the page, this is where things get a little trickier. So there are some summation formulas to kind of keep in mind. These summations can get huge. This n can be any number that you want it to be. It could be 100. It could be 100,000. It could be 1,000,000. It could be 1,000,000,000. Yes, it can be infinity, but then you start getting into like not like Taylor series, and you like try to figure out if it converges to something. We're not going to get that far. That's a Calc 2 skill. Okay. But we're just going to deal with real numbers here. So, do you guys want to add up 1,000,000 terms? Like actually 1,000,000 terms. Do you want to add them up?
No. Or 100 things.
Like typing into my calculator. 100 things. Do you even want to type that in?
No.
No. 50 things. Do you want to type that into your calculator? No. No.
I didn't even want to do 5.
Yeah. No. I get to like 3 and I'm like, no, I don't
Yeah,
want
like
to do
those
that.
ones on the front you
Yeah.
just did. You only did a few numbers, but if you want to do 100, like
Yeah.
from 1 to 100.
No.
So they're shortcuts.
Yeah. These numbers up here, like these formulas up here, it's a shortcut to it. Okay? So that's all that's going on. It's just a shortcut. Which is nice, like it really is. Because it makes your life easier in the end. Okay? So, what you could be given. Well, here I'll do like an example. We'll do this an easy one from up here. Okay. So do you see how this is I, right? And then this was to 3. So we'll do the same thing over here with this one. So like the summation from I equals 1 to 3 of I. Now I need to use the formula down here, right?
Yeah.
You guys try it. And then we'll compare answers to what we get. Okay?
Yeah, like when he did it on the front, you just did what, 1 plus 2
Plus 3. Yep.
But look at the formula. What's the formula say? It says to do
Yeah.
over
Yep.
2. Try that. Try it the different way.
Yeah, try it the different way. What should your answer be in the end? The answer here we got was 6. Yeah, it'll be 6.
I was just
Yeah, it should be the same. Yeah. So here was my work up here. So do you guys see how I followed it? Like this was n. This is the n up here. So I plugged 3 and then 3 plus 1 times 3 plus 1 over 2. So that's the same thing as 3 times 4 over 2, which is the same thing as 12 over 2, which just equals 6. So it checks out, right? I'm not a liar today. Tell the truth. Okay? So yeah. So now you might be given a more complex situation and be asked to solve it. Okay? So we're just going to do that. Okay? So first things first. Do you guys see how this is? Do you guys see how this is from I to n? So that means we can treat this n squared as a constant. So I'm going to do that. So on my first step, I'm just going to write from summation from I equals, that's a really trippy I, Mr. B, from I equals 1 to n. of 1 over n squared times I plus 1. Okay? That's legal. I can do that. Okay? It's the same thing. Same concept. Now remember, I can move this 1 over n squared to the front. No problem whatsoever. I can do that. So I'm just going to do that. 1 over n squared times the summation from I equals 1 to n of I plus 1. Okay? Now, in order to use my formulas, I'm going to have to do something with this I plus 1. Does anyone remember a property from the front page that lets me, that I can do that? Yeah, I can split them, right?
Yeah.
So, when I do that, I have to remember this 1 over n squared. I kind of have to put a parenthesis there, and then I can put my two summations. So that's just the summation from I equals 1 to n of I plus the summation from I equals 1 to n of 1. Now this 1 over n squared, it still applies to both of them. That's why I have to include these parentheses here. Okay? Because if you don't do that, it just it changes the expression. It would just mean that I'm only applying this 1 over n squared to this first term here. Now I have it in basic terms, so I'm ready to kind of substitute back in and substitute in these formulas over here. Okay? So I have 1 over n squared. Now this guy, he just equals n times n plus 1 over 2. Now this guy, he's just a 1. He's a constant. So up here I have a constant up here. That's just the same thing as the constant c times n. So in this case, it's just going to be plus n. Because 1 times n, that's just n, right? Okay. Now I want to distribute. So this is just going to be 1 over n squared of n squared plus n over 2 plus n. Whoa. Now I want to combine these together. So what do I need to multiply by the numerator and the denominator of n to do that? 2, right? Are you guys okay if I skip the step where I multiply both the numerator and the denominator by 2 and then just go straight into putting it all under one thing? Is that okay with everyone?
Yeah.
Yeah? Okay. That's what I'm going to do. 1 over n squared times n squared plus n plus 2n all over 2. Okay. Now I can reduce 1 over n squared, combining like terms. These two will combine together. Thank you. So I have n squared times n squared plus 3n over 2. Okay, now I'm just going to multiply through now because I'm ready to do that. So that's just the same thing as n squared plus 3n over 2n squared. Okay. Now, is there something that I can factor out of this numerator? An n, right? I can factor out an n, so that's just going to be n plus, I'm going to write that a little clearer. N times n plus 3 over 2n squared. Now I'm going to have an n drop out, and my squared is going to drop out. So my final answer is just n plus 3 over 2n. That's my final answer. Okay? We good?
Yeah.
Yeah?
Wait, on those, are you just dumb when you can't simplify anymore?
I don't know how to simplify further, do you?
Oh, there might
Yeah.
be questions on the homework
Yeah.
where they say now evaluate
Oh.
if n was 100.
Yes. Yeah.
Like now find the answer. What if it was a summation from 1 to 100? What if n was 100? So then you just
Yeah.
plug
Then you could just
into
plug
that.
100
Yeah, plug
into
100
those ends
into
of
those.
it.
Yeah.
Uh-huh.
Yeah. Mm-hmm. Yeah. Yeah. Plug
Yeah, that's what
100.
their
I think it's
questions
like, yeah. I think it's like plug 10 in, plug 100 in, and
Use
plug
your
like
result
10,000
to
in.
find the sums for n equals 10 or
Yeah.
100 or 1,000.
Yeah.
for sure.
Yeah, which is convenient. Okay. Any questions on that one? There's a lot of algebra in that step. That's what it is. Algebra. Yeah. Okay. So, why is this useful to calculus? Why? Why do we need to be learning about this, Mr. B? So, it's helpful because in calculus, a lot of times what we can do is sometimes we're asked to find the area underneath a curve. That's what we're asked to do. So, our solution to that is we're going to make a series of consecutive boxes. We can find the area of a box, right? What's that? Yeah, base times height, leg times width. Exactly, it's the same thing, okay? We're just finding the area of these boxes. That's what we're conceptually doing. That's what's conceptually is going on, okay? We can pick, now here do you see how it's picked, the point, it hits the graph as one thing? You see that? Now on my right-hand side, this one over here, it's picked a different way, right? On my left-hand side, this is called the left-hand endpoint. This is how it goes. And on my right side, this is called the right-hand side endpoint, okay? And that's going to help us kind of conceptually add up our boxes, okay? Now, we need to find, so we're given this function. How does this help us with a function? Now, we're only going to be doing right-hand endpoints in this class. Left-hand endpoints, I will show you how to find them. We're not going to be doing them, though, because they're hard and, like, make you want to cry. I mean, I don't. It's the same process as the right-hand endpoints, but, like, there's just an extra layer of difficult that I want to shield you guys from for right now. When I took this in actual college, they did not shield me from it, but I'm being nice. And, like, you don't need it. I'm going to show you how to do it, but this is how it goes. Okay? So the first thing that we need to find is we need to find the width. Like this stuff down here. Like how big is the space? How big is that? That's what we need to find out. Okay? Now the width is denoted by kind of the expression from b minus a over n. Now we get our a from here, and we get our b from here. So in this case, that's just going to be 2 minus 0 over n, and that just equals 2 over n. This is our width. Okay. The reason why it's over n is because eventually we're going to choose n many boxes, so we're going to choose as many boxes as we can in order to get an exact answer. That's why we need to go over n. That's what we need to do. Okay? And now, remember, we need to find our width, or our height. That's what we need to find next, right? But we're using right-hand endpoints. There's a formula for right-hand endpoints. And it's not in the book, but someone from last class basically kind of said that like they really wanted the formula. So we came up with one. So that's the same thing as like A. A is right here. A plus I times W, where W is the width. Okay. So in this case, that's just going to equal 0 plus I times 2 over n. So that's really just going to be 2I over n. That's what it's going to be. So that tells you kind of like our endpoints, like the numbers that we can plug in. Okay, that tells you the numbers that we can plug in. It doesn't actually give you the height quite yet. What we need to do is we need to plug in the height into our function f of x. Okay. in order to get the height. You need to plug this value in, or endpoint value in order to get the height. So really that's just 2I over n quantity squared. Okay? So this number right here, that's the height. Okay? Now, in order to get the area at that point, we need to take it times the width, which is just 2 over n, as we said earlier. Right? And now we have the width and we have the height. So now we need to find as many, and now we need to add those areas up. So what we're going to do is we're going to take the summation from I equals 1 to n. This part says we're just like adding all those boxes up. Okay? Now remember when I said we need to pick as many boxes as we can? We need to make as many as we can. So in order to do that, we're just going to take the limit as n approaches infinity. Hoofda. Okay? That's how we set it up.
That was just the setup.
That was just the setup. Now we need to solve. Okay? We can do it. We have all the tools in our tool belt to do it. I want to simplify first. So that's the limit as n approaches infinity of the sum from I equals 1 to n of 4I squared over n squared. I just distributed the squared there, of 2 over n. Now what I'm going to do is I'm going to just essentially combine these two together. So that's the limit as n approaches infinity of the sum from I equals 1 to n of 8I squared over n cubed. Okay. So now, do you guys see that this is an I down here, right? So I can treat the n cubed as a constant. I can also treat the 8 as a constant. So all I'm going to do is I'm going to rip them out. So that's the limit as n approaches infinity of 8 over n cubed times the summation from I equals 1 to n of I squared. Okay? Now I have it in terms of something that I can substitute in, right? I can substitute now by using these formulas up here. Okay? So I squared, that's just this big long monster right up here. We can do it. Don't be scared by it. I'm going to show you guys a trick of algebra. It's going to make your life so much easier. Okay? So I'm ready to go. So the limit as n approaches infinity of 8 over n cubed times n plus 1. I need to draw a line to keep myself straight here. Times 2n plus 1 all over 6. Okay? That's what we have going on. I just replaced the summation with what it equals up here. Okay? That's all I did between those two steps. So now I kind of want to reduce a little bit. So do you guys agree with me that this 8 will reduce down to a 4 and this 6 will reduce down to a 3? You guys see that?
Yes.
Okay. Now what I'm going to do is I'm going to switch the n cubed and the 3. That's all I'm going to do. Okay? I'm allowed to do that because of the commutative property. All right? It's legal. Okay? That's the limit as n approaches infinity of 4 over 3 times n plus 1 times 2n plus 1 all over n cubed. Okay? Does that make sense? I just switched the n cubed and the 3. That's all I did. Totally legal, totally fine. I can do that. Okay? Your book doesn't do it this way. Your book makes you distribute everything out. I think that's a major pain in the butt when you don't have to. Okay? If you would rather distribute it out, be my guest. But it's a lot of work, and I don't want you guys to go down that route. So now, this is where the trick of algebra comes into play. Do you guys agree with me that this n cubed is no more than n times n times n, right? It's the same thing, right? I didn't go anything wild and crazy. What I can do now is the limit as n approaches infinity of 4 over 3 times n divided by n times n plus 1 divided by n times 2n plus 1 divided by n. There's my trick. It's going to make your life so much easier, I promise. Okay? You guys see what I did there? It's the same thing, because if I multiply across the numerators, I'm going to get this, right? If I multiply across the denominators, I'm going to get this, right? It's the same thing. It works. It just makes your life easier. It's written a different way. Okay? So now I'm ready to take the limit, and well, not quite yet. I want to cancel something out first. This n over n, it drops out, right? So I just have the limit as n approaches infinity of 4 thirds times n plus 1 over n times 2n plus 1 over n. Okay? So now I'm ready to find a limit at infinity. Now, I remember taking the limit at infinity, but what do I need to remember I need to do? Divide by the...
Highest power.
Yeah, divide by the highest power denominator. I'm just going to do that quick. That's the limit as n approaches infinity of 4 thirds. This is going to be n over n plus 1 over n divided by n over n. And then this is going to be 2n divided by n plus 1 over n divided by n over n. Okay. Now I'm running out of room, so I need some scratch paper. Okay. This is online, so you can hunt it down there. Okay. Now I can simplify this out. The limit as n approaches infinity of 4 thirds. This will simplify down to 1 plus 1 over n. Now this n over n, that's just going to be 1, right? So I'm not going to write it. Like that's what it is. Okay? And now this will simplify out. That'll just be 2 plus 1 over n. And again, n over n, that's just 1, so I'm not going to worry about it. And I'm left with this, right? Now I can substitute in my infinity. So this is 4 thirds times 1 plus 1 over infinity times 2 plus 1 over infinity. What's 1 over infinity? 0. So that's the same thing as 4 thirds times 1, 1 plus 0 times 2 plus 1, 1 plus 0. So that's just the same thing as 4 thirds times 1 times 2, which is really just 8 thirds. That's your answer. Oofta. A lot of algebra there, isn't there? People are like crazy. Give me a thumbs up if it's doable. Give me a thumbs down if it's like crazy. Or in the middle if like I can figure this out eventually. Okay. Okay. It's mixed results. I promise the more you practice these, the better.
You only have 2 of those.
Yeah. There's only 2 on the assignment. So I was nice.
So it's not like you
No.
like 20 of those.
No,
questions.
no, you're not going to do 20 of those.
Obviously.
No. So that's the right hand endpoint. There's all. What?
I was gonna say that's probably good.
Yeah.
I don't have to show them.
Okay.
Just
All right.
be like.
The left-handed endpoint exists. If you want to see it, go look in your book. That's what it is. Okay. Yeah. So that's the right-hand endpoint. Okay.
Or they're gonna die.
Yes. Yeah. I'll show you the work for a left-hand endpoint. I'm not going to do it. I'll show you the work. It's like crazy. If I can find the piece of paper. Here it is. Here's the work. I took liberties. And you get the same answer in the end. Isn't that crazy? It's like magic to me. You get the same answer in the end, and you have to follow a different process.
Yeah,
So.
there's right hand and left hand because look
Yeah.
at these two pictures.
Yeah.
So one of the pictures, the rectangles were kind of underneath the curve, and the
That's
the
left
second
hand.
picture, see how the rectangle's kind of stuck
That's
up
right
above
hand.
the curve.
Yeah.
So that's why they do it two ways, but you get the same answer.
Yeah. You get the same answer in the end.
So it's easier to do the right hand endpoints like he showed you.
Yeah,
'cause
it
left
is.
too hard.
Yeah. Left is quite
Because
difficult.
it's just harder because there's extra variables in there
Yes.
to deal with, and you're
Yeah.
like, oh
And you're
gosh.
like, I don't. Yeah. This is unnecessarily hard. So yeah, right-hand endpoint does the same thing. Okay.
So what is H coding that? Is that the area?
Yeah, that's the area underneath the curve. So if I were to draw a picture, so this is 1, and then this is 2. It's going to be this area in here.
Okay.
That's what it is conceptually. So that's what's going on. It's just that area right there. Okay. Yep. Make sense? Sort of, kind of, maybe. The majority of your homework is based off of summation stuff. So don't get too worried about the ones at the end. Okay. Any questions? No. Okay. If not, I'm going to turn you loose on your homework assignment. It's on. It's out of your book. It's out of your book.